So, our objective today, our focus today, is that we're going to learn different types of bonding. The day before yesterday, we looked at valence electrons, and we talked a little bit about what the importance of valence electrons were. So let's review what valence electrons are. Celeste, can you tell us what valence electrons are? Where are they found?
Electrons found on the last energy level of an atom.
Very good. The electrons found on the last energy level of an atom. So Gavina, can you tell us where valence electrons are found again? Very good. That's shell the atom. And those valence electrons are special because, look at your notes from Wednesday. Okay? Who can tell me why those valence electrons are special? Yes, Oscar. Very good. They're in charge of bonding because they're in charge of the reactivity, right? Now, we also talked about how some atoms do not react. They are unreactive. They're the least reactive of all. Layla, can you tell me what elements those are? The least reactive. Okay, so those elements are found where on the periodic table? Group 18. And we also talked about another name for group 18. Luis, can you remember?
Noble gas.
Noble gases. Very good. Okay? So the reason we did that is because we're moving into this. So what we basically saw is that group 18 do not bond with anything. They're unreactive because we consider them stable. And they're stable because they have valence electrons. Remember that? So, basically, all atoms on that periodic table want to be stable. Every element on that periodic table wants to be stable. Every element wants to have a full valence shell. They want to be full. The thing is that they're not. Therefore, they are considered unstable. So let's look at the difference between stable and unstable. On Wednesday, I kind of alluded to the fact that the reason that things are stable and unstable, it has to do with the valence electrons. Okay? The maximum number of valence electrons that an element wants to have is 8. The reason that an element wants 8 is because 8 makes it full. A full valence shell is 8. Remember that we talked about the second energy level, and how many electrons can we put on that second energy level? 8. So that is why we consider it stable when it has 8. Excuse me. So something is stable when it has, or an element is stable when it has 8 valence electrons. And that's the maximum valence electrons that it wants. Unless it is an element that ends up having only one energy level. How many electrons can I put on the first energy level? 2. So if it's an element that ends up with just one energy level, then it is stable if it has 2. So if it has 2 on the first energy level, and that's all it has, then it's stable. If it has 8 on its last energy level, then it's stable. Some of the other classes asked me, but Miss, what about energy levels 5, 6, and 7? Those have like 18. Why is it 8? Well, the reason for it is because an atom is a 3-dimensional model. Okay? So even though we draw where the electrons are just going like this, just around a specific place, they actually have suborbitals. Okay, so you have 3 energy levels or 4 energy levels or so on. Each energy level has what we call like a suborbital. It's like a subsection. those subsections are S, P, and so on. So there's a little bit, it's more compartmentalized. The last compartment can only fit 8. Even though the last energy level can fit 18, within that last energy level, it has like 3 different compartments. The last compartment of that, or last section of the third level, you can only fit 8. So whenever you look at valence electrons, you're basically looking at the last level, or the last section of the level. So, it is always 8. If an atom is full, meaning if an atom has 8 valence electrons, it is considered stable or happy. That's why the elements in group 18 are stable. The noble gases do not react with anything else because they are already stable by themselves. But every other element on the periodic table is unstable. It's not happy because it doesn't have 8 valence electrons. It has 1, 2, 3, 4, 5, 6, or 7. Now, if it is an unstable atom, it is going to search out to be another element to become stable. And it does that by sharing or transferring electrons. So it either takes electrons, gives away electrons, or it shares its electrons, for it to have a full valence shell in order for it to be stable. Okay? Now, I gave you 2 sticky notes. Whoops. Gave you 2 sticky notes. We're going to do 4 of these. So you might want to either cut these in half or just divide them in half. I want this first general statement, I want you to make over this. So I'm going to give you about 3 minutes. Okay, about a minute and a half, talk to your table partner about what's important about these notes, and then a minute and a half generalization. Yes, Tristan?
We're only doing some half, okay?
Yes, so just do half because you're going to do 4 general statements today. Okay? So, talk, I want you talking to your partner, talk about what and what's important about these notes, and then come up with a general statement. Talk, talk, talk. Yes, sure. Or if you want, Tristan over here is fine.
Okay.
Or Lisa over there.
We make 2 statements.
I mean, not really.
Okay.
It's just you were right there in front of me, sorry.
Something with all that.
So you can do it. Yeah, I'll just put your hair and I'll put them in. I mean, don't have, move yourself over there. And then Tristan, I mean, that's gonna be your partner today. That way, we're all paired up and I just have one look at it.
So we just write general.
One general statement over this section of the notes. A general statement or a general statement over this section of the notes. Yes. All right, Giselle, could you share your generalization with us, please?
An enemy needs to have 8 valence electrons to be stable.
So, an element needs to have 8 valence electrons to be stable. Is that a good general statement about our notes?
Yes.
Yeah? All right, Vanessa, could you read us yours, please? Okay, an unstable atom will transfer electrons in its valence shell. That's a good one too, because it's transferring because it's not stable, right? So, now let's look at how does that transfer occur? okay? There are 3 types of bonding which we're going to look at. Is that a sneeze?
Yeah,
Wow,
that was
okay.
me.
I don't know.
That's my weird sneeze. Thank you for
A
making
little weird, yeah. Okay.
You okay?
Okay.
Okay.
So, we're going to look at our first type of bonding. Our first type of bonding is called an ionic bond. An ionic bond is basically a bond that is made from losing or gaining electrons. So, some of the atoms will lose some electrons and they're gaining some in order to become stable. When they do that, they become what we call ions. Ions are atoms that gain or lose electrons, and they're called ions because they are no longer neutral. When we first started to draw atoms, I told you, when we draw them as neutral atoms. Okay? Who thinks they can remember what neutral means? Raise your hand. Okay, Sid.
When they're like, when it's the same number of electrons, the same number of neutrons. I mean,
Protons, very good. So same number of protons and electrons. So Jackie, could you tell us what neutral means again? No charge, and they have no charge because? What 2 things are equal? In order for them not to have a charge, what 2 things are equal? Cindy just told us. Who can help her out? Okay,
The protons and the electrons are
okay, so Jackie, what's equal? Very good. So the protons and electrons are equal. That makes it neutral. So when we look at the periodic table, we are basically looking at atoms that are neutral. But when ionic bonding occurs, the reason it occurs is because it's losing and gaining electrons. It's losing and gaining electrons because it's trying to become stable. Okay? So Blake, can you tell us again what makes something stable? What makes an atom stable? Okay, but they transfer electrons to get how many? 8. Very good. Because they want 8 valence electrons. They want a full energy level, right? So, because they're losing and gaining electrons, they're losing positive or negative charge. Therefore, they become ions. So an ion basically is just a charged atom. It's either a positive ion, which is positively charged, or a negative ion, which is negatively charged. So, let's look at an example of ionic bonding. Bless you. If we look at this picture, we are looking at 2 elements, lithium and fluorine. Lithium is atomic number 3. So if it's atomic number 3, it has 3 protons, it has 3 electrons. So here I have my 3 protons and I have my 3 electrons. So these 3 positives basically cancel out the 3 negatives, right? That's why it's neutral. Then I have fluorine. Fluorine is atomic number 9. So I have 9 protons and 9 electrons. 9 positives and 9 negatives cancel each other out, therefore it's neutral. So these 2 are neutral, but they're not stable. This lithium atom wants 8 on this last energy level. So in order for this to be a stable atom, it would have to gain 7 electrons to be stable. Or it could lose 1 electron, and then if it only has 1 energy level, how many electrons can I put on that first energy level? 2. So would it have 2? So it would have 2, right?
Yeah.
So would this energy level be full?
Yes.
Yes. So even though it doesn't have 8, because it only has 1 energy level and it's full, it would be considered a stable atom if it lost 1. This one has 7 on its last energy level. It has 7 valence electrons. Well, it could either lose 7 and be stable, or it could gain 1 and be stable. Well, wouldn't it be easier to gain 1 thing than lose 7? Right? If we had several, everybody in here had different amounts of dollars, okay? And Vanessa had $7, and I had $1, and one of us had to have 8, wouldn't it just be easier for me to give her a $1 than her a $7 to me? It would hurt me less to give up $1 than her to give up 7, right? She can do much more things with $7 than I could do with my 1. Correct? So, basically it's the same principle. It's easier to give if you have less amount, and it's easier to take if you have more. Okay? So, if lithium gives up an electron, so now it only has 2 electrons and 3 protons. What charge are the electrons? Negative. And what charge are protons? So it has 3 pluses and 2 minuses. So 3, positive 3, and negative 2. If I add those together, what do I get? A positive 1, right? So that's why it becomes a positive ion. If it loses an electron, it becomes more positive because it has more protons in the middle. For fluorine, if I gain an electron, now I have 9 protons in the middle and 10 electrons on the outside. So 9 positive, negative 10. So I have positive 9 pluses, and 10 electrons, negative 10. So negative 10 and a positive 9 gives me a negative 1. That's why this becomes negative. So, Joanna, can you explain to me why lithium is positive? Why is lithium here, this one, not this one, why is this lithium positive? No, well it is stable, but I'm asking why is this considered a positive ion? Who can explain to me why this is positive ion? Luis.
Because there's 3 protons, then minus 2 electrons equal.
You're right. So it has 3 protons and it has how many electrons?
2.
And what charge are electrons?
Yeah.
So
3 minus
you're right. 3 minus
2 equal 1.
is
Positive 1.
positive 1. Okay, so Joanna, could you explain to me now why this is a positive ion?
Because I'm negative positive 1.
Very good. Okay, so now Yuriti, could you tell me why fluorine is negative? Very good, because that's more electrons than protons. Okay. So Eric, can you tell me why fluorine is negative?
Because negative charge and positive.
Very good. So do you see how if you have more negatives than positives, then you're negative, right? If you have more positives than negatives, then you're positive. So when lithium gives up an electron, it becomes positive. When fluorine takes an electron, it becomes negative. Well, think about it. Positive and negative. Now these are opposite charges, right? Don't opposite charges attract? Right? If I take a positive end of a magnet and a negative end of a magnet, don't they attract each other?
Yeah.
That's why these bond together. These two, when lithium loses an electron and this one gains an electron, become positive and negative. They attract to each other, they bond, and they make the compound lithium fluoride. So that's how we get compounds if they're going through an ionic bond. Because one of the elements becomes positive, the other element becomes negative, positive and negative attract, they attract to each other, and they make a completely new compound. Okay? Question, Tristan?
Is that why if you run electricity through it, the electrons and electricity will disperse like in water?
Yeah, basically any like for example, you were asking about batteries the other day. Okay? And most of the compounds that are in batteries are ionic compounds. Because they have those charges, therefore they allow the electricity to move through it. They create electrical current. Okay? Any other questions over this? Alright, so now we're going to think about this. I have a positive, I have a negative, and they join. So if I have low numbers, 1, 2, or 3 valence electrons, am I going to lose those or am I going to gain? Lose. Now if I have 5, 6, or 7, I'm going to gain. So let's look at the periodic table. So group 1, is it going to lose or gain? It only has 1. Lose. Group 2. Group 13. Lose. It only has 3, remember? So lose. Now, we're going to talk about group 14 later. Group 17. Gain because it has 7, right? Group 16. It has 6. Group 15. It has 5. So, if I look at the periodic table and I look at elements, what two types of elements are making ionic bonds? Left, right. Metals and non-metals. Very good. So, I know by looking at losing and gaining that metals and non-metals go through ionic bonding. Okay? That's important. Write it down. Okay? So, what two elements go through ionic bonding? Metals and non-metals. Very good. So, Ursi, what two metals go? What two elements go through ionic bonding? Metals and non-metals. So, by looking at what or how many valence electrons they have, you can predict that an ionic bond is going to occur between a metal and a non-metal because it's from left to the right. So the left side likes to give, the right side likes to take. Okay? So I'm going to stop once again. Go back to your sticky notes. So the other half of the sticky note, I want you to talk to your partner, table partner, and come up with a general statement for ionic bonding. Just one. So a general statement, a general station for ionic bonding. But I want you talking. I need you talking. Talk to your partner. Come up with a good general statement. Okay, Orlando, could you read us your general statement?
I put that. No metal bond.
Okay, bond, and let's add to that, to make what? What type of bond? Which type of bond are we talking about?
Finally.
Very good. Okay, so you make sure you include that. Okay, good. Blake, could you read us yours, please?
I have the bonding situation using the
Okay, that is an awesome generalization. It includes everything we just talked about. Okay, so you want to make sure that you're trying to include everything. Very good, Blake. All right, so now we move on to our next type of bonding, which is covalent bonding. So in ionic bonding, we're losing and gaining electrons. In covalent bonding, now we're sharing. Okay? Sharing is caring. Sharing is caring. Okay? Covalent, start with a C. Sharing is caring. Covalent sharing. Okay? I'm trying to give you a way to remember that covalent is sharing. So, covalent bond is bonds that share electrons. Sharing is caring. Caring starts with C. Covalent starts with C. Got it? Alright. So, covalent bonding is the sharing of electrons. Now, in covalent bonding, this can happen between two different elements or atoms, or two of the same type of element or atom. When it occurs between two of the same type, we call those diatomic molecules. So diatomic molecules are basically molecules that were formed from the bonding of two of the same type of element. Examples: H2, N2, O2. H2 is two hydrogens, N2 is two nitrogens, O2 is two oxygens. So in diatomic molecules, what you're seeing is you're seeing a sharing of electrons, but it's a sharing of electrons with the same type of element. Now, remember we talked about in science, you want to look at prefixes, suffixes, sometimes that helps you out. The prefix di means the same thing as the prefix bi, bi. So what do you think it means?
Both.
Both or two. Okay? Bicycle. Two cycles. Okay? So the prefix di means two. So diatomic means two atoms. Atomic means atoms. So two atoms. Aren't there two here? Aren't there two here? Aren't there two here? These three are called diatomic molecules because you have two of the same type. Okay? And they are covalent bonds. Now, all covalent bonds are not diatomic molecules, but they can be. So the example I gave you for a covalent bond is H2. So here I have hydrogen. I have one proton, one electron, no neutrons. Another hydrogen, one proton, one electron, no neutrons. Well, what does this hydrogen need to have in order for it to be stable? Reese?
2 electrons.
2 electrons. Why not 8?
Because it only has one energy level. And you can only fit
Very good. So Gavino, could you tell me once again why or how many electrons this one needs to have?
2.
And why not 8?
Because helium has 2 and
Okay, this hydrogen.
oh,
Why would hydrogen not need 8? Luis, can you repeat your answer again?
because you can only fit 2 electrons on the first energy level.
Okay, so Gavino, can you tell me again?
you can fit 2 electrons in the same.
Very good. So, since hydrogen only has one energy level, then it's going to be stable with just 2, because that's all you can fit on that. Okay? So, when they covalently bond, what they're going to do is they're going to share these 2 electrons. Okay? Now, when we look at this, you have one proton. So these are 2 hydrogen atoms. But the electrons are just going to be shared right here. So basically, they're going to stay in an area where both of them get the charge. Thank you. And they are attracted because since they have to share them, those electrons are basically kind of just stuck in this area. And because they're stuck in the area, they're stuck together. Okay? So, in covalent bonds, we are sharing electrons. Okay? And you're bonding because those electrons are kind of stuck in a specific place. So if they're stuck there, they're there. They're not going to move. It's basically like when you do puzzles, you take a puzzle and you stick one into the other one and it just kind of sticks there. It sticks there because it fits, right? Okay, same thing. This electron just fits there, so it fits like a key. That's why they're stuck together in this case. So in ionic bonding, they stuck together because positive and negative attract. In covalent bonding, it's almost like a key. They're stuck together because these two have to be there. Yes?
How would they rotate? Would it be like an
You would still have a rotation of moving. Like they would still be kind of moving.
Would it be like an infinite sign? Like going from one to the other?
It could be, it doesn't necessarily have to be. But yeah, they would be moving sort of around those two nucleus, the two nuclei.
So the ionic bonds, like, they're not connected or something?
They are connected, but they're connected because of positive and negative. These are connected because the two electrons have to stay together.
But I was talking about, you can put it together.
Because what I did here is I want you to know that the reason these are bonded is because the positive and negative are attracted to each other. The electron that is getting over here, it's over here. It's not going to be over here anymore because it gave it away. So the electrons aren't the ones that are attached. Here, they're attaching because of positive to negative.
So like you don't have to put it together. Like,
No. Here, they're going to be attached. So these are attached because of electrons being attached. These are attached because positive and negative attract each other. Okay? Alright. So take a minute and a half. I want you to come up with a general statement for covalent bond. Talk. I wish you to hear you talking. You're talking about how can you generalize? How is this different from ionic bond? What basically would you look at in order to know that it's a covalent bond? And as soon as you finish, I want you to start thinking, I want you to predict, by looking at what I wrote over here, which two types of elements join as a covalent bond. So just predict in your head. I'm going to talk about it in just a second. So just predict in your head, think about it. We're going to talk about it in just a second. You know? Good. Okay, so first let's talk about your general statements. Adan, could you read yours for us, please?
Covalent bond, it can happen when two different atoms.
I'm sorry?
A covalent bond can happen when there's two different atoms.
Okay, very good. Alright, Joanna, could you read yours, please?
They bond the same type.
They bond, I'm sorry?
They bond in the same type.
Okay.
And
And
they
what are they doing to bond? What are they doing to bond?
share.
Very good. I would include that in there.
And
Okay, and they share electrons. Very good. So, who thinks they know which two type of elements bond in covalent bond? Tristan?
Oxygen?
Okay, but what types? Remember, the other one was metals and nonmetals. Which two types do you think bond here? Well, look at what I have. I have H2, I have N2, I have O2.
Non-metal?
Nonmetals. Very good. Okay? H2 is a nonmetal. N is a nonmetal. O is a nonmetal. Water, H2O. H-O. Nonmetals. So water is what type of bonding?
Non-metal?
Correct.
Covalent bonding. And because they're both nonmetals. Very
so
good.
only 9 metals?
Yes. Yes, so covalent bonds occur between nonmetals. okay? They share their electrons and that's how they bond with each other. Alright, now we're going to come to the very simplest one, but complex one at the same time, which is the metallic bond. The metallic bond's a little weird. Simple but complex at the same time. And the fact that a metallic bond occurs because of the distribution of electrons in an atom. Distribution basically means where the electrons are within that atom. So sometimes this metallic bond is called the sea of electrons. Sea of electrons meaning the electrons are out there around the nucleus. Okay? When they come in contact with another element that has electrons out there outside the nucleus, because those electrons are sort of in proximity, they call it theirs. Okay? Let me give an example. So, your parents pay for the house or pay rent on where you live, right? So they're the ones that are paying the taxes, they're the ones that are paying everything, right? So it's their house. But whenever they say, hey, where do you live? Do you ever say, well, my parents' house is so-and-so? Or do you say, oh, my house is here? But you don't pay for it. Why is it your house? Because you're their child. You're just kind of around them, so it's yours just because you're there, it's yours, right? Metallic bonds are like that. Okay? So basically a element comes in contact with another element. They're sort of in the same proximity, so they consider those electrons that are in that proximity theirs. And they have it, so they bond with them. Okay, so just because they kind of come near there and the electrons are there, well, they're around here, so I'm going to call mine. Just like you call it your house, even though you don't pay for it. Okay, you call it your house. You don't say, oh, my parents' house is here. It's at my house. But you don't pay for it, but you consider it yours because you live there. Correct?
Yes.
Even though you don't pay, you consider it yours. Metallic bonds, think about it that way. The electrons are around the vicinity or the area. Therefore, they are considered theirs, and in that consideration, you bond two elements there. Now, by looking at the title, this occurs between what type of elements? Metals. Two metals. Okay?
So what if I like they're around
What basically, whenever they're around each other, if, like for example, let's say beryllium has 2 electrons, 2 valence electrons, so it needs either to give away 2 or gain 6, right? Alright, when it comes in contact with, let's say, tellurium has 6 valence electrons. So 6, 2, and 6 equal 8, right? So it really doesn't give the 2 to tellurium, but because it's sort of in that area, it says, oh, tellurium 6 are mine. So I have 8. Just because they're in proximity. So because they're close to each other, they end up bonding to each other by the sea of electrons. Okay? That's the simplest I can make it. It's actually pretty complex, but we don't need to get into that. So just think about it that way. It's your house because you live there, not because you pay. Okay? Alright, so last thing, go ahead and write your last general statement for metallic bond. And I'm going to pass out your white paper for your special assignment. I'm going to go ahead and give you your special assignment today. It's for next week. Is that helping y'all any if I give you the special assignment on a Friday instead of waiting until Monday?
Yeah.
We have the weekend.
We have the weekend to do it.
I'm not saying that it's going to happen all the time, but I will definitely try as much as possible to do so. To do that. I will, and just kind of hold on for a second. here's one, even though they broke the, sorry. Here's one, but they broke the little pin. Okay, so let me go ahead and give you the special assignment for next week. It's called the bonding triangle. On your tables, you have this blue equilateral triangle. What you're going to do is you're basically going to take that triangle, put your white paper on it, and trace it. The reason I'm making you trace it like that is because in order for this to work, the triangle has to be an equilateral triangle. Okay, Ursi, what's an equilateral triangle? There you go. All three sides have to be the same. So that's why I'm getting you to trace it. Did I give you a white paper? Okay. I'm going to get you to trace it. You're going to cut it in just a second. But I'm going to go ahead and give you the actual assignment. So you'll be tracing in just a second. I really want you to stop. Stop tracing. I want you to pay attention so you know what you're doing. Okay, we have done folded twos and folded fours. In folded twos and folded fours, you're basically comparing and contrasting 2 or 4 things, right? The bonding triangle is just a way for you to compare 3 things, which are the 3 types of bonding. So, we're basically going to do it sort of the same way as we've done the folded twos and folded threes, where on the front, you're going to have a triangle like this. Once you have your triangle, you're going to fold it into a smaller equilateral triangle. So you're going to end up with something like this. On the first flap, you're going to give me a picture and a word that helps you remember covalent bonding. So you're going to draw a picture, and then a word or a phrase that helps you remember what covalent bonding is. You cannot use the word covalent, bonding, ionic, or metallic on the front of these flaps. Okay? On the inside of the flap, that's where you're going to write the word covalent bonding, and you're going to give me an explanation of your picture and your word. How does this picture and the word help you remember what covalent bonding is? Then, your next flap, picture word for ionic bonding, the word ionic bonding, explanation and word for ionic. The next flap, picture and word for metallic bonding, inside, same thing, explain your picture and word. So any questions over the outside flaps? How do you fold it? Just going to fold it into small triangle. Basically, this is what you're going to get first, right? You're going to take one of the sides, fold it in to where the tip basically touches the middle of the other side. Take the other one, fold it over, take the other one, fold it over. So you're basically just going to do a small triangle. Alright, now, the inside. This is where you need to pay attention because people mess up here. So this inside triangle, you're going to take and draw a smaller triangle there, which will you'll end up with 4 smaller triangles inside the big triangle. In this triangle, you're going to give me the differences between the 2 words that they touch. So here, I would write the differences between ionic bonding and covalent bonding. Here, I write the difference between covalent and metallic. Here, I write the difference between metallic and ionic. So in these outside ones, you're writing the differences between the 2 that touch that triangle. Everybody see that? Okay. All right. Then in the middle, the center triangle, you're going to tell me how are all of these 3 similar? What's the same between all 3? Okay? Question, Tristan.
Do we use color?
Yes. With all special assignments, remember you have to have at least 4 colors. Okay? So any questions on your special assignments?
You're gonna like pictures.
Yes, I am. Any questions over the assignment?
No.
Now, I will have pictures of that posted online as well as the lecture for today. So for the rest of the period, which is like about 5 minutes, you can work on your skill sheet, or you can start, I would start tracing that triangle and cut it.